monopolist wants to do, obviously, is maximize their profit. So the monopolist is going to buy that product, Y, for some price C of Y. And their goal is to come up with a price for that product. That price is going to be denoted V of Y. Now, we're going to assume that there's some function B of XY, which governs how much benefit a consumer X obtains from product Y. Now, the consumer wants to maximize the benefit they receive minus the price they pay. So they're going to maximize, they're going to choose the Y, which maximizes this quantity, which is just their benefit minus the price they pay. And sort of a key aspect of this model is the consumer gets to choose the product, and the monopolist gets to influence that choice by varying V. The monopolist's problem is assign the costs, so choose V, that maximizes this functional. And this functional represents the price they obtain from selling at price V minus the cost that they pay for that product. So one common example is cars, but there's also phones, airline ticket pricing are examples of things that satisfy this model. So to make this a bit more concrete, to narrow things down to a case that we have the best chance of understanding, the prototypical case is you just assume your benefit is the inner product of X and Y. And we assume the cost the consumer pays, sorry, the monopolist pays, is Y squared on 2. And then some further simplifications we're going to make for this talk is that our domain is just the square for much of the talk, and our measure mu, which represents how the consumers are distributed on the domain, is just the Lebesgue measure. So immediately we get that this choice made by the consumer now becomes a Legendre transform, because our U of X is the supremum of X dot Y minus V of Y. Straight away, we know that U is a convex function. And whenever our function U is differentiable, the choice of product the consumer makes, which on the previous slide I denoted by YU, is now the derivative du of X. So rewriting the original functional, which had a V term as an X dot Y minus, so it had a V of Y, and at the maximum point, we can rewrite this as a U minus X dot Y. An entirely equivalent reformulation is minimize the following functional. We've just argued that U is necessarily convex. The other thing we're going to enforce is that U is non-negative. And what this represents is the monopolist not being able to charge so much that a consumer receives negative benefit. And the interpretation is if the monopolist were to do so, the consumer would just not play the game. They wouldn't participate. So this region where U is equal to 0, we call the non-participation region. So that's the economics problem. And now for the rest of the talk, we're just interested in this minimization problem and what we can understand about it.
So I was slightly confused because it says find a non-decreasing U, but you said U should be non-negative convex.
Yes, yeah, you're right. The non-decreasing, that's another assumption, and it just represents that we've translated, so our space of products is a subset of the positive quadrant, because that's our Y. If our Y is in the positive quadrant, our du is positive, so our function's gradient has positive components and our function is increasing. So this problem has seen a bit of interest, first from economists and more recently from mathematicians. So a brief history is up there. Muser and Rosen were some of the first to consider sort of the mathematical aspects of this problem, and they focused on the one-dimensional problem. Roche in 1987, he did the same transformation we have to this one involving the Legendre transform. Armstrong, and another economist who considered this problem in its early days, proved a very interesting result that I'm going to talk about a bit, called the desirability of exclusion. Roche and Chonet were the first to look a bit at this theory of convex orders that we're going to do. And then more recently, some regularity aspects of the problem were considered. So notably, Cale and Lachan-Robet, they proved C1 regularity to the boundary under an absolute continuity condition on your distribution mu, and some convexity conditions on domain. This was strengthened in some unpublished work by Caffarelli and Lyons. And then more recently, just before I arrived in Toronto, Robin and Kelvin were considering what we can say about Euler-Lagrange equations in what I will explain as the difficult region of this problem. So before I start telling you about my results, I want to do two things. The first is that I want to convince you that this is an interesting model in the sense that you can read off some fairly significant conclusions of economic significance quite simply. That makes it an interesting model, right? If it has serious consequences. And second, I want to explain to you why it's a mathematically difficult model to study. So to do the first, to convince you that there's some economically interesting consequences, I'm going to talk about this result of Armstrong called the desirability of exclusion. What that result says is in this setting we're working in, if the monopolist optimizes their profit, then they price out a positive measure set of consumers. So that was the region where our function is 0, where consumers say you're charging too much, I don't want to buy your product. That set has positive measure. And we're going to prove that under a couple of reasonable assumptions. The first is that our domain X is strictly convex, and the second is that our X and our Y lie in positive. So this the proof I'm going to present of this result, it's kind of going to follow completely from this little lemma, which I know from the book of Evans, but is reasonably popular and probably appears in many sources. He calls it the differentiation formula for moving regions. And it just says, if you're computing an integral over a moving region of a function, which also depends on time, well, then the derivative is computed as follows. To compute the derivative over the moving region, well, you have a differentiation under the integral sign, and you have a boundary term from your moving boundary. And that's just integrated against your function times the velocity of your domain. So this little lemma will prove, we'll make quick work of this theorem of Armstrong's. So I'm going to leave that lemma at the top, and then I'm going to show you the proof of Armstrong's result. Conceptually, what this is saying is if everyone can afford your product, you can make a bit more money by charging a bit more and pricing out the bottom portion of people. How we prove that, though, is we're going to assume we've got our minimizing function u. And this proof should not be too difficult to follow, but it's very indicative of the type of perturbation arguments that are kind of bedrock to our approach. So we've got our minimizing u, and what we're going to do is we're going to drop it down a little. That means each consumer gets a little less utility because we're charging a bit more. But our minimization problem takes place over the space of non-negative functions. So if I've dropped down my function, I have to set it to 0 wherever it gets negative. So I'm replacing my original u with this new one, which is u minus t everywhere that's non-negative and 0 elsewhere. What's the new monopolist's profit? Well, we put our ut back into our functional, and that ut, it has the same derivative everywhere it's positive. The only difference is now we've got a u minus t, and our function is 0 wherever u was less than t. So now we integrate over the set u greater than t. So this is the new profit. And what we know is that because our original problem had a minimum at 0, the derivative of that with respect to t at time 0 has to be 0. So this is sort of a very standard perturbation type approach. You go ahead and compute that derivative. Well, the differentiation under the integral sign, it's just going to come out as a -1 from that t. And then we get at time 0, it's -1 times the set where u is greater than 0. And then we've got our boundary term. And I don't care what that integrand is. I just care that we've got a boundary term. Now, this is what the derivative comes out as. When I rearrange it, I'll get the set where u is greater than 0 is less than the integral of this boundary term. Now, the set where u is greater than 0 has positive measure, because if not, your monopolist isn't selling any products. They're definitely not maximizing. So this set has positive measure, which means this quantity has positive measure. The only way that quantity can have positive measure is if we're integrating over a set of positive measure here with respect to Hausdorff n minus 1. So the boundary of the set where u is greater than 0 inside our domain, which is equivalently the boundary of the set where u is equal to 0, has positive measure. And for a increasing function on a strictly convex domain, that implies your set U, where U is equal to 0 has positive motion. So quite quickly, you get some, I think, rather like startling conclusions. If you buy the model at all, if you think it's reasonable, you have to not sell to a portion of your population. Otherwise, you're not maximizing the profit. The other thing I said I wanted to do was explain why this is a difficult problem. I mean, if you have at least a little experience in PDEs, you'll recognize that that integrand, the Lagrangian we're minimizing, is not too horrific. It should just come out as a Poisson equation. But what I want to make a comparison with is two other really classic problems. One is minimizing the Dirichlet energy, and one is the obstacle problem. So minimizing the Dirichlet energy is one of the oldest PDEs there is. We want to minimize the integral of du squared, which is one of the key terms we've got up here, subject to some boundary condition. Now, solutions of that are going to be harmonic functions. They're going to be analytic as smooth as you'd like on the interior of your domain. The obstacle problem, on the other hand, it asks you to minimize the same integrand, minimizing the same integrand, and the only additional condition is we enforce that U is greater than G, where G is going to be some function representing an obstacle. And suddenly, for reasonable families of G, for smooth G, our solutions won't even be C2. So we've gone from analytic, infinitely many derivatives, to not even having two derivatives at each point. So the picture behind that is here's some boundary data. We can solve Laplace's equation, and our solution looks good and it's smooth. Then we want to jam in an obstacle. And what we're going to enforce is that our solution now lies above the obstacle. When we do that, it'll come out like something like this. We can show it's C1, and wherever it's not touching the obstacle, it's still harmonic. But on the equality set, your Laplacian is whatever the Laplacian of your obstacle was. So if I have a case like this, where my obstacle is, say, a parabola, so its Laplacian is, if it's minus x squared, it's minus 2 on n, then suddenly the Laplacian of the function is minus 2 on n on that region. So that's where our function is not C2, because inside the region where you touch your obstacle, your Laplacian is 2n, outside it's 0. So your second derivatives are discontinuous. So what I want to say is, well, the integrand we're minimizing, it's worse than that. It's got two conditions. So minimize the integrand by itself with some appropriate boundary conditions. And the Euler-Lagrange equation, it's just n plus 1. Laplacian u equals n plus 1. So up to adding or subtracting a parabola, your function's harmonic and smooth. With the convexity, this should be with the non-negativity constraint. We're pretty much in the world of obstacle problems. So we'll have a region where your function is 0, and we've just explained that always exists. And then we'll have a region where your function is positive and it satisfies your delta u equals n plus 1. So certainly just for the obstacle problem, we expect solutions of this monopolist problem to not even be C2 across that free boundary. But then things get worse because we have this convexity constraint as well. So we've got, in our problem, we've got two, we have two different regions that may prove troublesome as far as the regularity is concerned. One is where this non-negativity condition is binding, and one where this convexity condition is binding. So the first thing we want to do today is understand a little bit of the structure of each of those regions. So in analogy to the obstacle problem, when you want to study the obstacle problem, you split your region, your domain into two regions. One where you're touching the obstacle, where the obstacle condition is binding, and one where you lie strictly above the obstacle, where that condition is not binding. We're going to do the same thing, but with regards to convexity as opposed to the obstacle. So for any convex function, we can take our support plane at a point. So that's just the equation for it. And we can consider the set where you touch your support plane. We call that the contact set. And the way we're going to divide our domain is according to the dimension of each contact set. So we call curly xi the set of x such that the contact point at that set point has dimension n minus I.
Yes, that should be X. It should go to the next slide.
That one? Yeah, it should. Thank you. So this n minus I, you just got to get your head around it real quickly. What it means is, for example, for the 2D problem, x2 is points where your contact set has dimension 0, so that's points of strict convexity. So the obvious picture for a convex function is x0 is points where your function is affine on some open set. X1 is point where your contact set is a line segment, and finally x2 is your points of strict convexity. So we want to understand each of these sets. These are going to be our sort of coarsest classification of the behavior of the function. So what we're able to say is the following. We take our minimizer u and we define each of these sets. And I've phrased this theorem for n dimensions because this particular part of our theory works fine in n dimensions. But what we have is that, first of all, x0, which is this set we defined as just where your function is flat, well, it's just the set where u is equal to 0, i.e. what that first point is saying is there's no other portions of your function where it's affine on an open set and positive. So the only region where consumers, a positive measure set of consumers buy the same product is when they're buying no product. Okay, on our set of strict convexity, our xn, we can do what we usually do, and we can obtain an Euler-Lagrange equation. It's delta u is equal to 3. And we can show that that set xn is an open set. And so u is its C infinity of xn. Now, finally, the regions where you're convex but not strictly convex, these are the most difficult to analyze. For as far as this theorem's concerned, we'll say more later, but as far as this theorem's concerned, what we can say is that if you take a contact set, so in the 2D case, this was the region consisting of line segments, then it has to hit the boundary. So if you're not strictly convex and you're not 0, you're in a contact set which extends all the way to the boundary. And so this has an interesting enough economic interpretation, and it's the following. Those points are points such that the consumer is buying a product that's bought by many other consumers, whereas strict convexity corresponds to products bought by a single consumer. All those products bought by multiple consumers lie on the boundary of your set of products sold. So I want to take a look at how we would actually prove this result. And the big underlying aspect of this model that's most difficult to work with is you can't just do what you usually do for calculus of variations and take an interior perturbation. Because when you perturb a convex function on its interior, you might end up with a function which is not convex. So we can't say that the value of our energy functional or our monopolist profit functional is necessarily larger like we usually do. We can only do one-sided perturbations. And the two that we're going to make the most use of are presented in this theorem. So if I've got my minimizer and I've got any other admissible function, then I can define, I can derive these one-sided Euler-Lagrange equations. And that's them there. The proof, well, for these one-sided perturbations, you can do it essentially as you usually would for the calculus of variations. We take any other admissible function. We note that all our constraints on the function are such that the set of functions satisfying those constraints forms a positive cone. So I can consider these convex perturbations only for t greater than 0, though, and we only need it for example, t is 0, 1. We use minimality and we compute a one-sided derivative at the origin. And there's no real difficulty about the fact that this derivative has to be one-sided, because when you go ahead and consider your original function, it's just your profit function, once your u and u tilde are fixed, is just a polynomial in t. So there's no difficulties. But this is what we have to work with to try and understand the behavior of our solution. So let's see how we can do that to prove, for example, the first point.
Sorry, I get two inequalities here.
Yep, that's a good point. This little explanation is just for the second. And what we're doing is we're differentiating our function at the point u, where u is the minimizer. But I can also differentiate my function at the point u tilde. Because it's convex, I also obtain information on the derivative at that point as well. And both are quite useful. This one is particularly useful when you're constructing perturbation functions, because often you can explicitly construct the u tilde to have properties you desire. So here's how we would prove, for example, that first point, that the only region where you're affine on a set of positive measure is the set where you're zero. We suppose otherwise, we suppose there's some open set on which you're affine and positive. And we construct a perturbation function. The idea behind this perturbation function is as follows. You take the set on which you're affine, you drop down the support plane, and then you patch up your function so that it's still convex. I'll say a bit about the construction of this in a second, but it's a lot harder to drop convex functions down than it is to lift them up. But once we've done this, what's our perturbation function going to satisfy? It's going to satisfy that u tilde minus u is negative on that whole contact set. And so it's going to be some negative constant minus h, and it's going to have the same derivative, again, on that entire contact set. Now, there'll also be these points here off the contact set where we have a little less control of our function. Certainly, it doesn't have the same derivative. But if we denote the set where you're changed by this curly x u, then that set where you've changed, but you're not in the original contact set, has measure 0. And we're going to be able to prove that, in fact, that set's measure goes to 0 at least order h. That's a technicality, but it means when we put our new function into our perturbation inequality, well, on px naught, we've got u tilde minus u is negative, and du tilde minus du is 0. So this entire integrand becomes negative h. Now, we do have this extra bit where we don't have the same control of our function, but we know that, first of all, on that set, the region over which we're integrating is order h, and our integrand is also some order h. So for h sufficiently small, we're going to contradict that inequality. So even though we can't do the usual very obvious perturbations, we can be a bit more explicit. And just briefly, how we actually construct this one is, well, I said it's hard to drop down convex functions, but what you can do is you can switch to the Legendre transform, you can lift up there, and then you can switch back. So if I consider the Legendre transform of this, I'm going to obtain a point whose subdifferential contains this entire contact set. So your Legendre transform has a little cone. I can lift up my support to my Legendre transform at that point, and I've lifted up my Legendre transform so that when I switch back, I've dropped down my original function. And then it's just a matter of checking, as constructed like that, you have the correct growth estimates on the set where you're not just a drop down. Okay, so I'll say a bit, that was how we do the classification on x naught. I'll say a brief bit about x2 and x3, but so x2 and x1, but not quite as much. We integrate our perturbation formula that we previously obtained. And for strictly convex points, we can do that entirely the interior. So after integration by parts, there's no boundary term. And our perturbation inequality comes out like this one here.
Is really interesting.
Yeah, yes. Thank you. Yeah, I switched between m dimensions and thank you. When I do this, I obtain this perturbation inequality. And again, I can't just perturb by any function, but I can be a little more deliberate with my choice. And I can say, well, if the Laplacian of u was less than 3, I can bump up my parabola a bit, so its Laplacian is less than 3, then drop it down, and I've obtained an interior perturbation, which is a perturbation down, so this term is negative, but my Laplacian u is still less than 3, so this is positive, and we contradict that again. And then you can go the other way as well. You get that Laplacian u is equal to n plus 1 throughout this entire open set. The Caffarelli and Lyon's result implies that your function, we should have w to infinity here, but that's enough to get that in fact you're smooth by the regularity theorem.
So this is still true in dimensions.
Yeah, this is still true in n dimensions. Because we want w to n and we've got w to infinity. Okay, and the description of x1 is I think the most enjoyable from a description of the techniques. So what we want to do is prove that these contact sets hit the boundary. We suppose otherwise that there's some contact set strictly contained in the domain, and we consider the section of our convex function. So we take its support and we lift it up, and it's strictly contained in the domain for some small upwards translation of our support. Now we can modify our previous perturbation argument, which was the one that let us obtain Laplacian u equals 3, to work at any point in a section. You don't just need strict convexity, being an interior point of a section will work. So then what have we got? We've got a section of a convex function in which Laplacian u is equal to 3. We can bootstrap that again to our function is smooth in the section. Now it's a convex function, so its second derivatives are non-negative, and by differentiating Laplacian u equals 3, its second derivatives are harmonic. Now, in a section for a convex function, at some point every second derivative is positive. So we've got a non-negative harmonic function which is positive somewhere in the section, thus it's positive everywhere, and certainly our function does not contain a flat portion. So the hypothesis we made that we had a strictly contained section is wrong. So those are the main ideas that give us our classification theorem. The next thing we want to ask is, well, first of all, can we better describe these intermediate regions? And can we say anything about how these regions partition the domain? So we're going to take a look at now this example from the start, where we're just looking at the problem on a square. So some numerics due to Mirenberg, which are on the left here, strongly suggested that the solution looks like this. You've got your omega naught. This is Mirenberg's notation, and I borrowed the picture from him, so he's called it omega naught. We call it x naught down the bottom. You've got your x2 up top, where your function is strictly convex. And then there's your x1, where your function is affine along lines. And there's a couple of distinct portions of x1. One is where your contact sets are parallel, and one is where they branch out and start to become non-parallel. And these numerics, they're kind of recent. They're from 2016. For quite a long time, people did not realize that these additional regions existed. They thought it was just a parallel region. But you can prove, there's a couple of different proofs that no, that cannot be true. You cannot have just this parallel region with a flat boundary on the set where you're strictly convex. So our goal is to both understand this region and understand the behavior of the function in this region. So what we're going to do is we've just said that our one-dimensional contact sets all hit the boundary. So we can parameterize our x1 by these contact sets, and we can parameterize those by where they hit the boundary. So where they're parallel, that region's been relatively well understood for a long time. Your function is essentially just a function of one variable, and the Euler-Lagrange equations in that region have been well known for some time. In the region they're not, in the region where the contact sets are not parallel, then we can in fact do better than parametrizing by just where you hit the boundary. We can parameterize by the angle you make. So we're going to take a look at, for example, those foliations where, or sorry, those contact sets that hit the left boundary and which are not in a region where the contact sets are parallel. So we're going to parameterize by the angle it makes with the vertical, with the horizontal, sorry, and the length along that particular contact set. So we introduce these as new coordinates. And our key assumption that U is affine along these line segments means we can write U in this way. And we're going to let capital R of theta denote the length of the contact set that makes angle theta. So we want two tools here. The first is that parametrization. The second is these results you get from having measures in convex order. So our perturbation inequalities that we had earlier, after integrating by parts on the whole set, they become as follows. We've got our Laplacian term, and we've got a boundary term. And we've got this particular inequality that holds for every admissible function, so every non-negative convex function. What this says, up to that condition of non-negativity, is that our measures Laplacian u minus 3 dx and du minus x dot n are measures in convex order. And the definition of convex order, there's a couple of equivalent ones, but one of them is just two measures are in convex order if when you integrate them against a convex function, one is always bigger than the other. So by that definition, we clearly have two functions in convex order. And an old result due to Cartier, Fell, and Mayer says that, well, when you've got your measures in convex order, we can actually decompose them and obtain the same perturbation inequality holds when restricted to every contact set. So there's a caveat here, which I'll say in a second, but what we previously had over the whole domain, we now get on each contact set. And I've abused some notation. Usually we use this restriction symbol for just a measure restricted to a set, but here I'm using it for the measure conditioned to lie on that set. But this is what this theorem of Cartier, Fell, and Mayer gives us. It's often referred to as the sweeping theorem. Some minor modifications are necessary to deal with the fact that that theorem holds for convex functions, whereas that theorem holds when your functions are in convex order, whereas we've sort of only got it for convex order with non-negativity. But you still get this result. You just get it for, as opposed to all convex functions, you get it for ones that their positivity set is a subset of the set where your U is positive. So now we have two things. We've got our useful coordinates on each section, each contact set, and we've got a differential, our perturbation inequality on each contact set. So we can combine these two things. And the way we're going to do that is we're going to compute the Laplacian in our new coordinates, and we're also going to compute that conditioning of those measures. Once we do that, we're going to get the perturbation inequality on the third line. And this is starting to look a bit more concrete as far as both our function u is concerned and our coordinates are concerned. So this proves to be quite useful for studying the function. Two examples of what we can get out of this quite quickly. An interesting, well, I claim it's interesting, and I should have a bit more to say about that, but a particular relationship between the deficit in your Neumann boundary value and how long your contact set is, as well as the Euler-Lagrange equations governing the behavior in X1. So these were previously derived by Kelvin and Robert using quite complicated perturbations of convex functions, whereas this use of the sweeping theorem lets us obtain a new approach to these. Now, by working with the new Euler-Lagrange equation, the new perturbation inequality, and the other relations we get from it, we're able to almost completely prove the form we conjectured here, this one that Mirambeau's numerics suggest. And I'll explain what I mean by almost completely prove it in a second. But what we can show is that, first of all, as conjectured, the non-participation region, it's an equilateral triangle in the lower left corner. Then you've got a region where your contact sets are parallel and orthogonal to the diagonal. this is the region that was already known. And then you've got a component of x1, which intersects the left-hand boundary, in which the contact sets are not parallel, and which the new Euler-Lagrange equations are satisfied. And then you've got a symmetric component below the diagonal. So one above the diagonal, one below. And finally, in x2, it's a simply connected set in which U is a smooth solution of Laplacian U equals 3, and your Neumann boundary condition is satisfied. So there's two caveats in which I say we've been able to almost completely prove these conjectures. The first is that there's the possibility that this is one we completely expect to rule out with a little more work, is that your upper portion of omega-1 might hit 0 and then bounce back. So it might not just be this very clear decay of the length of your sections. There might be a second sort of component of that. That's not what we expect, and then we're working on ruling that out. The other caveat, though, is this classification of x1, it only holds for our A, which you'll recall is the coordinate of the lower left corner of this square. It only holds for A sufficiently large. So at the moment, it's A greater than 5/2, which is probably not sharp, but there will be some critical A. So the reason for that is, or we expect there to be some critical A. The reason for that is we've said the contact sets have to intersect the boundary. Now, this point here has coordinate AA. If you consider sending AA to 0, then we can reflect. At that point, we're at the origin, and we can reflect and work on the square of size 4. And that's going to have certain symmetry properties. And in particular, once we've reflected, all these points will be interior points of our problem. So it can't be where contact sets end. So the problem for A equals 0 will not have these x1 regions. And we expect that to manifest at some point for some positive A, conjecturally. But we don't know sort of a lower bound on what that A will be. Okay. I want to say a bit about the regularity of the free boundary problem. I also considered the possibility of touching on regularity theory for more general problems, but I won't do that in the interest of time. So another equation that we can derive from that sweeping theorem and our new coordinates is the following. It's that 3 minus delta U is equal to 3r minus 2r on h dash cos theta plus r. And if you stare hard enough, this is quite an interesting relation, because it says that along a contact set, there's, first of all, let me emphasize that the denominator is positive. So that doesn't change sign. This says that 3 minus delta U, where we know 3 minus delta U equals 0 is the Euler-Lagrange equation in the strictly convex region. It says at some point at r equals 2r on 3, so 2/3 of the way along the contact set, your Laplacian or your 3 minus delta U switches from positive to negative. So that means along that whole boundary of x1 and x2, your 3 minus delta U switches from 0 in the strictly convex region to strictly negative in the x1 region. So that says that your Laplacian is discontinuous along that free boundary. And so not only along the U equals 0 set is a point where your C11 lock being optimal manifests, but along that whole upper boundary, that's a point where you're C11 but not C2. So we can say a bit more about this discontinuity. We can say it occurs entirely in the U sub RR coordinate. I can't go into much detail, but the reason is if you consider along your line segment, if there was a discontinuity of your second derivatives in the direction orthogonal to your line segment, then your function would look flatter on one side and sharper on the other. That's what it would mean for your second derivatives to have a discontinuity in the direction orthogonal to the line segment, and such a function can't be convex. Once we know the discontinuity in the second derivatives happens along URR, we know that the Lipschitz first derivative UR is different from the interior and the exterior directions. We can extend both of those into the other domains as new Lipschitz functions and obtain that our boundary is the set where these Lipschitz functions intersect. And by that discontinuity result, it's the set where a Lipschitz function is say equal to 0, but has non-vanishing subdifferential. A particular non-smooth version of the implicit function theorem due to Clark says any such set is a Lipschitz hypersurface. And then we obtain that that boundary is a Lipschitz hypersurface. So I'm going to skip over this extra material and go to a couple of ideas for future work. So once we've got Lipschitz, it would be nice to know that you're better than Lipschitz. You're not better than Lipschitz everywhere, though. If you look at the picture, certainly conjecturally, your boundary is at most Lipschitz there. So what we'd like is a result that's similar to these ones for the obstacle problem, which is that the set where you're not Lipschitz is very small. I think we're far enough off that I wouldn't confidently conjecture just how small that set of singularities is going to be. And then we've got our domain classification for n dimensions in general domains, but we don't have Euler-Lagrange equations for x1 in those regions. Those would be very good to have. And then finally, it would be good to describe this partitioning of the domain for more general densities. Here it was just for your consumers, it distributed according to density equal 1. So there's lots of future work to do. Thank you all for listening. And if you have questions, let me know.